Hello, I'm Sugyung-moon from the DTM Lab. Today I'll be presenting a review of the paper titled R&D Partner Recommendation and Network Prediction Using Pattern Data. The DOI and keywords of this paper are as follows. The primary purpose of this study is to propose deep learning framework uses bibliometry, semantic texture, and network-based features to recommend R&D partners. The outline of presentation is as follows. As technological change accelerates and product complexity increases, it has become more difficult for firms to innovate relying only on internal resources. Therefore, inter-firm R&D collaboration has become an important mechanism for accessing external knowledge and accelerating innovation outcomes. However, existing R&D partner selection often relies on expert judgment. While this approach can consider strategic fit and technological relatedness, it may also introduce subjectivity and reinforce partner selection among familiar organizations. To address this issue, prior studies have used patent data for partner identification. These studies can be broadly classified into three approaches: bibliometric approaches, textual analytics, and network-based methods. Although prior studies have used bibliometry, texture, and network, each approach captures only a partial perspective. Bibliometry methods provide structured indicators, texture analytics capture semantic aspects, and network analysis models structural dependencies, but none of them alone fully explains R&D partner selection. This creates a need for an integrated framework. Since deep learning is well suited for combining heterogeneous features, this study aims to develop a knowledge fusion deep learning model. Specifically, the model integrates three types of patent-based features in order to recommend R&D partners and predict future collaboration networks. In R&D collaboration, partner selection is not simply about finding similar firms. It requires a balance between complementarity, which provides new capabilities, and sufficient similarity, which enables communication and knowledge absorption. From the perspectives of RBV, KBV, and network theory, partner selection can be explained by three key mechanisms: technological capability, knowledge relatedness, and existing network relationships. Patent data are suitable for operationalizing these mechanisms because they include both structured metadata and unstructured technical text, and co-patenting relationships can be used to reconstruct collaboration networks. Therefore, prior studies on patent-based partner selection can be classified into four streams. First, bibliometric analysis uses structured patent indicators such as citations, classifications, and co-assignee data to assess technological strengths and innovation capacity. Its strength is that it provides quantifiable indicators, but it may not fully capture emerging or fast-moving technologies because it depends on patent classifications and citations. Second, semantic texture analytics uses text mining and NLP techniques to extract technological insights from unstructured patent text. This approach can capture more fine-grained technological meaning than bibliometry indicators, but earlier studies often relied on shallow models or keyword matchings. Third, network analysis uses the structure of co-patented networks to predict collaboration potential. It is useful because it captures structural proximity, but it may also reinforce path dependence by favoring already well-connected firms. Last, prior studies have developed hybrid approaches to overcome the limitations of single methods. These approaches provide a richer assessment of collaboration potential by combining multiple perspectives. However, most existing studies integrate only two dimensions. Therefore, this study addresses this gap by proposing a knowledge fusion deep learning approach that integrates bibliometric, texture, and network-based features within a unified framework. Figure 1 is the overall research framework. In step 1, the study constructs an applicant-based collaboration network using only co-applicant patents. In this network, each organization is represented as a node, and an edge is created when two organizations jointly apply for a patent. In step 2, the study analyzed the structure of the R&D collaboration network using standard network measures. These include average degree, average weighted degree, graph density, characteristic path length, and average clustering coefficient. In this study, collaboration potential is evaluated through four dimensions: technological strength, R&D openness, R&D linkage, and collaboration effect. First, technological strength captures a firm's technological capability and innovation capacity. Second, R&D openness reflects how willing a potential partner is to collaborate and share expertise. Third, R&D linkage measures the historical strengths of collaboration between organizations. And last, collaboration effect represents the expected synergy from a potential partnership. The final indicators used for bibliometry analysis are presented in Table 2. The purpose of this step is to measure the semantic relatedness between firms' patented knowledge. By calculating semantic texture similarity scores between patent documents, the model can capture technological proximity that cannot be identified from structured patent indicators alone. To do this at scale, the study uses an expert-based patent experta procedure. This approach combines the accuracy of a cross-encoder with the scalability of a bi-encoder. In implementation, a Roberta cross-encoder was first fine-tuned and used to generate similarity scores for about 8,000 patents, producing roughly 33 million document pairs as civil labels. Then the trained bi-encoder was applied to the full patent corpus to compute large-scale STS scores. Based on STS scores, the study defines two key measures. First, technological similarity measures how closely related the technologies of two organizations are. It is calculated as the average STS score across patent pairs between the two firms. A higher value means that the firms share more similar technological domains, which can support communication and knowledge transfer. Second, technological breadth measures how diverse an organization's own patent portfolio is. It is calculated as the average semantic distance among its patents. A higher value indicates that the firm covers more diverse knowledge domains, which can support exploratory innovation. The study applies link prediction to estimate the likelihood of future collaborations in the R&D collaboration network. It also uses centrality analysis to evaluate each organization's structural position within the network. For link prediction, the study calculates 9 representative measures across local, quasi-local, and global approaches. These measures capture both immediate neighborhood information and longer-range structural signals. In addition, degree, betweenness, and closeness centrality are used to identify important organizations and brokerage laws. Overall, these network-based features help the model understand not only whether two firms are technologically related, but also whether their network positions make collaboration likely. R&D partner recommendation is formulated as a binary classification problem. A value of 1 means that two organizations collaborate, while 0 means that they do not. The model uses input features from three sources, and these features are calculated from period 1 from 2018 to 2020, and the model predicts whether collaboration occurs in period 2 from 2021 to 2023. Overall, the DNN is designed to run complex relationships among heterogeneous patent-based features and use them to recommend future R&D collaboration opportunities. The performance of each prediction model was evaluated using standard metrics, and the most effective model was then selected to predict future R&D collaboration networks and recommend suitable potential partners for individual firms. The study visualized the results using two dimensions: technological complementarity on the x-axis and the DNA-generated recommendation probability on the y-axis. This allows firms to understand not only whether a partner is likely to collaborate, but also what type of innovation strategy should the partnership may support. In particular, lower technological complementarity indicates higher similarity, which is useful for incremental improvement and exploitation. In contrast, higher technological complementarity expands the search space and supports more exploratory innovation. The study focuses on 23,796 self-driving vehicle patents filed between 2018 and 2023, including 5,237 co-applicant patents. From this data, the authors identified 412 organizations, which resulted in 84,666 potential collaboration pairs. For model training, the study calculated 29 descriptive features from period 1. The target level was whether collaboration actually occurred in period 2. The dataset was split into training and test sets, and the model was optimized using five-fold cross-validation and optional. Since the data were highly imbalanced, it also applied a positive class weight to improve the model's ability to detect actual collaboration cases. The model evaluation results are as follows, and Figure 3 shows the precision Likert curve of the prediction model, highlighting the inherent trade-off between precision and Likert. In practical terms, firms can adjust this balance depending on their strategy. If they want to discover more potential partners, they may prioritize liquor, while firms with limited evaluation resources may prioritize precision to reduce false positives. So the key takeaway is that the model provides a flexible decision support tool for R&D partner recommendation. The purpose of this comparison is to examine whether combining different types of patent-based features actually improves prediction performance. The baselines use only one type of information. As shown in the table 4, the integrated model generally outperforms the single feature models. This result suggests that R&D collaboration cannot be fully predicted from only one perspective. The study uses common baseline models and applies the same data split and evaluation protocol for a fair comparison. As shown in the table 5, the DNA model demonstrates substantially better overall performance than the classical models. This suggests that the DNA is better able to capture complex and nonlinear relationships among bibliometric, texture, and network-based features. However, the study also notes that overall performance is still constrained by the severe imbalance between collaboration and non-collaboration cases. Therefore, while the DNA improves prediction performance, the imbalance issue remains an important limitation. The results showed that the number of partners slightly decreased, but the intensity of collaboration increased. In other words, firms tended to work with fewer partners but formed stronger relationships with them. At the same time, the increases in clustering coefficient and graph density, along with the decrease in characteristic path lengths, suggest that the network became more cohesive and better connected. Overall, the SDB collaboration network appears to be moving from fragmented collaboration toward stronger clusters centered around a few key firms. This provides an important baseline for predicting how the collaboration landscape may evolve in the future. Based on the existing network structure, The prediction model was applied to patent data from 2021 to 2022 to forecast prospective collaborations. The model identified 390 potential partnership pairs. Compared with the observed period 2 network, the predicted network shows higher connectivity, higher clustering, and greater density, while the characteristic path lengths decrease. This suggests that the SDB collaboration landscape is likely to evolve into a denser, more cohesive, and less fragmented network, where previously weakly connected firms become more integrated into larger collaboration clusters. The study illustrates the practical value of the model using Toyota as a case study. The model identified 70 potential R&D partners for Toyota, including both firms with prior collaboration histories and newly recommended partners with previous collaboration records. An important point is that the model does not simply recommend familiar partners based on past relationships. It can also identify previously unconnected partners, which expands Toyota's search beyond its existing collaboration network. Therefore, the partner selection map helps firms distinguish between partners for strengthening existing capabilities and partners that may offer new technological opportunities through complementarity. To enhance model interpretability, the study applies SHIP to evaluate the marginal contribution of each input feature to partner recommendation. The results showed that important features are not concentrated in only one category. So this result confirms that R&D partner recommendation requires a combined understanding of technological capability, semantic alignment, and network position. The main contribution is that the proposed framework provides a structured decision support tool for R&D partner selection based on observable patent data. It also expands the search beyond existing collaborators by using the partner selection map and the network prediction module. In particular, the framework helps firms identify partners that fit different innovation objectives. Similar partners can support exploitation-oriented collaboration, while more complementary partners can support exploration-oriented collaboration. However, the study also has several limitations. It relies only on USPTO patent data, does not include validation by industry practitioners, and does not apply GNN-based models. In future research, these limitations can be addressed by using more diverse data sources, strengthening external validity through validation by industry practitioners, and extending the model with GNN-based link prediction models. Thank you for listening.